This video is an introduction to double integrals over general regions found in section 15.2 of our text. So our goal in this section is to learn to compute the volume of a solid bounded above by the surface z equals f of xy and bounded below by a region that is not necessarily a rectangle. That is, we want to compute the double integral over d of a function f of xy where the region d is not a rectangle. Our strategy is to set up the double integral, but find different expressions for the x and y bounds of integration. Now here are some examples of what the region D might look like, and these are what we'll call type 1 regions. Notice here that in each region D, the x values are bounded between two numbers a and b, and the y values are bounded between two functions g1 of x and g2 of x. Therefore, when we set up the double integral over d, we'll have for the outer integral, our dx integral, we'll use the bounds a to b. And for the inner integral, our dy integral, we'll use the bounds g1 of x to g2 of x. A couple of comments. Remember, these double integrals represent a volume, and therefore our final answer should be a number. In order to ensure that that happens, the bounds on the outer integral must be constants, numbers a and b. If we want to include functions in our bounds, the functions must be on the bounds of the inner integral. Another comment. Notice that in the region D, y is bounded below by the function g1, and therefore the lower bound of our integral is g1. And D is bounded above by the function g2, therefore g2 is the upper bound on our integral. The key to getting these bounds correct for our integrals is to sketch the region D. Let's do an example. Let's compute the double integral over d of x squared minus y, where d is the region bounded by the curves y equals x, y equals 2 minus x, and x equals 0. Alright, so first we want to sketch the region D. And here it is. Notice we have the lines y equals 2 minus x, y equals x, and of course x equals 0 is just our y-axis. It's important to find the intersection points because that helps us with our bounds. We can see what they are from our sketch, but let's go through it algebraically as well. We simply want to know when 2 minus x equals x. So we add x to the other side and divide to see that we have our intersection point at x equals 0. Therefore, our double integral over d can be written like this. Notice that x lives between the numbers 0 and 1, and y lives between the functions y equals x and y equals 2 minus x. Great. Now, that inner integral is with respect to y, so we'll integrate with respect to y first. That will give us x squared y minus a half y squared. The outer integral, of course, just tags along. And now we're going to evaluate as we always would, from our lower bound of y equals x to our upper bound of y equals 2 minus x. So we start by replacing the y with 2 minus x, and then minus what we get when we replace y with x. To integrate, we'll do a little bit of algebra first. Nothing interesting happened in this step other than just multiplying things out and combining like terms. We then integrate with respect to x and evaluate from 0 to 1. So our final answer would be negative 5, 6. Great, let's look at another one. Here we want the double integral over d of y e to the x, where d is bounded by the curves y equals the square root of x and y equals x. We always start with a sketch of the region D, so here it is. Let's find our intersection points algebraically. We want to know when the square root of x equals x, squaring both sides, that's when x equals x squared. We subtract the x to the other side, factor out the x, and see we have intersection points of x equals 0 and 1. Therefore, our double integral over d can be written like this. Notice that in the region D, x lives between the numbers 0 and 1, and y lives between the functions x and square root of x. We first integrate with respect to y, so we get the integral from 0 to 1 of 1/2 y squared e to the x, evaluated from y equals x to y equals the square root of x. So we replace y with the square root of x minus what we get when we replace y with x. Now, if you think back to your end of Calc 1, beginning of Calc 2 days, you may recall that in order to compute these integrals with respect to x, we're going to need the technique of integration by parts. And in fact, to do the integral of x squared e to the x, we'll have to do integration by parts twice. And that's certainly doable. It's not a hard thing for us to do, but it does prompt us to think that maybe there's an easier way, a different way to approach this problem that would make our work go a little bit faster. And that brings us to what we call type 2 regions. So here, the region D, we see that the values of x are bounded between two functions, h1 of y and h2 of y, whereas our y bounds are bounded between two constants, c and d. And if our region looks like this, then we can set up our double integral over d so that the outer integral is our y integral. The outer integral, remember, has to have bounds that are constants, so from c to d. And then our inner integral will be our dx integral, and that will have our functions h1 of y to h2 of y. Notice the curve on the left, h1 of y, is our lower bound. The curve on the right, h2 of y, is our upper bound. So with this in mind, let's return to that example 2 that we had previously. Now we're going to want x equals functions. So we'll rewrite our equations as x equals y squared and x equals y. Again, we start with a sketch and we find the intersection points. We subtract y over, factor, and see that our curves intersect when y equals 0 and 1. So this time, we'll set up our double integral over d, thinking of dy on the outside. So y is bounded between the numbers 0 and 1, and x is bounded between the functions y squared and y. So this time we'll integrate with respect to x first. We get the integral from 0 to 1 of y e to the x, evaluated for x between y squared and y. So we replace x with y minus what we get when we replace x with y squared. And this is actually a much easier integral than the one we had previously. Yes, this first integral still requires integration by parts, but the second integral, instead of requiring integration by parts twice, now is a basic u substitution. So here's what we'd get when we do the integration by parts and the u substitution. Evaluate y from 0 to 1, and we get a final answer of minus 1/2 e plus 3/2. If you're curious, here's the scratch work for that integration by parts on that first integral, and the scratch work for the u substitution on the second integral. Great. So moving forward, you'll see that when you set up these integrals over the region D, you'll have a choice to make. Do you want to integrate first with respect to x or with respect to y? And then once you make that choice, that will help you decide how you want to set up your bounds. Remember that the outer integral must have bounds that are constants, and any functions must go on the bounds of the inner integral. And we'll play a lot more with these in class together. Thanks, guys. I'll see you then.